Hello and welcome back to Calculus1 Saturday edition. We are talking about fundamental theorem of calculus, which is where we put our semester into one box. So far we had good definitions, street definitions, right, for concepts. And now it's time to put and tie all of that together in one spot and see what we get out of it. Now, before that, we are going to say that the entire Calc 1 consisted of limits, derivatives, and integrals. And they all had their use. Limits, right? Compute y value in their own way. Derivatives measure change. Integrals eventually give us area under the curve. Also accumulation. So having all of these things, put out there, the calculus consists of all of these things, and you don't get to learn more concepts than this. Calc 2 will have these what I called summations and series, and that's, guys, going to be just your expansion on the summation notation we already learned. Calc 3 is going to bring three-dimensional calculus with triple integrals and partial derivatives, stuff like that. But you're done learning the basic concepts, and we just need to tie them together. So we started by using limits to define the derivative function by limit h goes to 0 of f of x plus h minus f of x over h. And then we defined the definite integral through the limit of n goes to infinity, summation I goes to n, I goes from 1 to n of f of xi delta x. So we see that we have the derivative, the integral, the limit, right? Those are the three heavy hitters of calculus. And there they are, right? All together on a pile. And we said that we can use derivatives, right, to calculate instantaneous change. And we can use these guys to calculate area under f of x. Or this is change of f of x, right? So this is what we had so far. Now today we're talking about the fundamental theorem of calculus and the way these guys work together. FTC, fundamental theorem of calculus, has two parts. Part 1 is the one you already know, the definite integral. Integral a to b of f of x dx is equal to any antiderivative f of x computed from a to b, which computes as f of b minus f of a. That's the part 1. We did that part in our 5.2. There is nothing else to add to it. It's the part 2 where we are, there is stuff to add to this. We will after the definition, but you know this one. Now part 2 is the one that we are considering, and that is the one that says that the derivative of the integral of a to x of f of t dt is equal to f of x. That's a big one. So when you look at the fundamental theorem of calculus, I'm going to box this thing. And when you look at this, right, it's this two-part theorem. First part is definite integral, and the second part is also definite integral, but it does have derivative in it. Now let's focus on the part two, because we spent an hour and a half earlier on part one. We know how to compute it. We know what it means. We have to add more stuff to it, though. But let's first focus on part two. So for part two, what we see here is we don't see a capital F on this side like we see it here, right? We see the lowercase f, which is this lowercase f from here. So when you look at this, it somewhat looks like that the derivative and integral cancel, and you just have f equals f, which is exactly what happens. If you perform this calculation, using part one, you are going to get the answer. Now, this is one of the rare proofs that we do in vanilla calculus, but it's very easy, and it's, again, fundamental for understanding of what Calc1 gives us at the end. So if I start with the derivative of integral a to x of f of t dt, and we use this t as a dummy variable just so we don't confuse x's all over the place. Copy your derivative, and now you know that the integral is going to give you the antiderivative of t computed from a to x, right? So we integrated and we got what we have by part one, right? Isn't that what you get by part one? Now, obviously, if this is t, it will be f of t. If it's, I don't know, g, it will be f of g, and so on. So whatever the variable is, our variable was t, so we get f of t. We also know how to compute this, right? We compute it by plugging in the upper minus the lower. And now, when you apply the derivative, you get f of x minus 0. Because the derivative of a number, right, f of a is a number. See, f of x is a function. And the derivative of that one is the original function. We know that from 4.9, right? So let's go orange. From here to here is a 4.9, where we said that the integral of f of x dx is equal to f of x plus c, which means that the derivative of capital F of x is just f of x. And that's how you check your problems, right? That's what we use to check. So we know that the derivative of f of x is this f of x here. So you integrate, you get your antiderivative, and when you differentiate antiderivative, you get your original function back. So we know that. And then f of a is a number, right? So f of a is constant, a number, and then the derivative of that one is 0, obviously. So we get f of x as the answer. So yeah, in some sense, we canceled the derivative. So if you are, I mean, the integral and derivative. So if you are to ask, what is the derivative of integral, I don't know, 3 to x of tangent x to the fourth, t to the fourth dt, your answer is simply tangent x to the fourth. That's it. There is nothing to compute, there is nothing to do there, because we have the formula for that. And in some sense, this formula tells us that derivatives and integrals cancel each other out. Yes, they undo each other, right? They're opposite operators. So one pushes the function one way, the other one brings it back where the other one changed it, right? So you can see that in that game that we had before with x squared, right? We said the derivative of x squared is 2x, which meant that the integral of 2x dx was x squared, and we put plus c on it. And if I want to check, I say the derivative of x squared plus c was 2x, which is right there. But ultimately, that was this. So we already know that these two are opposites of each other, and now we'll just write that as a formula, which is part 2. We write it as a formula, and this formula tells us technically that integrals and derivatives cancel. Now that's a huge deal, because it opens the doors to create differential equations, which are the basic stepstone of all of the sciences we have. 100% of everything we have comes from differential equations. Because when you are observing some system, the system changes. So you are observing that system in the eyes of the derivative. And differential equations are equations which contain derivatives. Now, some of those equations are directly solved by integration, which is opposite operation of the derivative to give us the formula. So 100% of science going forward is you observe the world, you come up with some function that has some formula, that equation that has derivatives in it, because you were observing change. Guys, you're either observing change or you are not observing change. You're observing a constant. There's nothing else. And when you're observing a constant, there is nothing to learn there, because a constant, it's always the same. It will be the same in 100 years. But when you are observing change, right, that's your derivative. So when you have the derivative, you observe the change and you have the derivative, then you actually have something that's called differential equations. And then that differential equation is obviously solved through integral, because remember, for equations, you are doing the opposite, right? To dig all the way down to x. Well, now to undo these things, you will be using integration to undo derivative to get to the equation that you're looking for, which is solution, which is the formula that governs the concept you are observing. So these are very simple concepts when you look them up from that point, and then you just have to learn the details. Details of modeling, details of solving differential equations. But all of your physics formulas and all of your chemistry formulas and all of your whatever formulas you ever looked at, they're all differential equations at one point in time that mathematicians solved, and then physicists said, okay, this is a formula in physics. But if you know calculus, and we've seen that along the way, physics it becomes a joke, because once you are able to derive your formulas and once you're able to compute those formulas, right, then you don't need to, then you can just take the concept from physics, right, and put them together with differential equations and calculus, and you get your own formulas. You can reinvent 100% of physics if you know mathematics sufficiently. Now, obviously, once you know physics, you can start developing chemistry and engineering and all of these kind of things. That's the order in which things are figured out. It's always mathematics to give us abstraction. Then that mathematics is applied in physical reality, which is called physics. And then you get chemistry, biology, and everything else eventually, right? So what's the furthest away from it? Medical field. Medical field is less developed than biology. Biology is less developed than chemistry. Chemistry is less developed than physics. Physics is less developed than mathematics. Mathematics is always first. and then give a couple of years for physics to catch up, give, sometimes a couple of hundred of years for physics to catch up, then give some time for chemistry to catch up, give some for right? So that's why our medical field is still technically nowhere, right? We are still patching people instead of really fixing the problems, right? You know that a lot of stuff that have like engineering, mathematics, physics in on the bottom of it, the fix is 100%. The fix is instantaneous. The fix is right. So you patch the road, or you patch the bridge. You swap the graphics card if it dies in the computer, right? And there is no recovery time. There is no try this might work, try that might work. We know exactly everything that works because all of that is math and physics. Now, the other fields that are still developing in and trying to implement mathematical formulas, like let's say biofield, and then the entire medical field being subset of that one, they have a very slow progress, right? People still have to go to surgery, then there is a recovery time, right? Imagine if you were just able to swap a heart like you swap a processor in a computer. 15 minutes, no recovery time, you just boot the computer, is working. Now, processor is not the heart, processor is the brain, but it doesn't matter. Pick whatever human part. There is a rejection rate, there is this drug might not work, this procedure might not work, we still have people dying from disease, people are freaked out about corona, right? If the medical field was developed to the point where, the other engineering fields are, none of this would be a problem, right? You flip a switch and you're 100% instantaneously, just like when you swap alternator in your car, when you swap graphics card, let's say, in your computer or anything like that. So now going back to this, mathematics is the first, right, in line. And what you do here is, once you understand how these things work with the fundamental trinomial calculus, for instance, right, you can develop literally everything else. So going back now to fundamental trinomial calculus, there is another thing that quite nicely shows why these things are opposites of each other, and that is, I did write them before, I'll write them again, the definitions for the derivative and definition for the integral, the area under the curve. Now, if anyone would tell me, is there something that really shows us here how come these two cancel each other? That would be great. Like, think about this, the way they look, and tell me, is there something there that tells you why these two should cancel each other out, right? Why these two operations cancel each other out, so that when you write the derivative of the integral cancels down to the original function. Like, why is that happening? Looking at the two formulas up there, right here. Can anyone tell me that?
Well, the limit on the integral is going to infinity, and the limit on the derivative is going to 0.
Perfect. That's one of them. Very good. One limit goes to infinity, one limit goes to 0. Anything else? Come on, guys. It's really obvious. I mean, you are gonna facepalm when I tell you, but let me see if you can figure it out without me telling you, because it's really obvious. Come on, guys. Looking at the two formulas, why would they cancel each other? Like, what are the things that cancel each other in mathematics? Can you find them? And it's really obvious.
The division.
And what?
And
Division, that's talking about this one, as opposed to what from the integral one?
the subtraction.
Well, division and subtraction.
Multiple.
Yeah, multiplication. We should all be able to see that there is divided and then times. Right? So this age, if you are learning this from a different textbook, they actually have it as delta x. So it's much easier to see even. And you can see that over here you are dividing and over here you are multiplying. So those are opposite operations. And then someone mentioned subtraction. Yes, it's right there. And what is it is? That's addition, right? Right. So you see how opposite these are in every aspect, right? You have limits are going to 0 and infinity. Then you have division and multiplication are opposite, and subtraction and addition are opposites. These formulas are complete opposites of each other. And they both feature delta x. As I said, if you are to pick up, let's say, Larson book, which is the one that I like the best in calculus and one I learned from when I was learning calc for the second time. The book gives you as the limit delta x goes to 0 of f of x plus delta x minus f of x over delta x. No age. They give you this delta x. And then when you compare that with the derivative, with the integral formula right here, right, you see, oh, in the upper one I'm multiplying by delta x, in the red one I'm dividing by delta x, right? So all of those concepts kind of click together and it's much easier to understand. But it's enough for us to understand here that these two formulas are complete opposites of each other just because we have this operations, right? And I can now maybe color code them or something where I'm going to, right, circle these pairs in red, circle these pairs in blue, and maybe go with orange with the division and multiplication, and just write opposites, right? I'd like opposite pairs. So fundamental theorem of calculus tells us that derivative cancels integral or integral cancels derivative. Obviously much more on that when you start differential equations, if you start differential equations, and go from there. And the last part that I really need to talk about is this area issue. It's very important issue, guys. And here is immediately an example. So integral 0 to pi of, 0 to 2 pi sine x dx. You would immediately say, that's easy. That's a joke. And it is. It is a joke. Integral of sine is negative cosine x computed from 0 to 2 pi. Like, we don't even have to do anything special. But now when you plug this in, you get negative cosine of 2 pi minus negative cosine of 0. Now, you know your trig, luckily. So negative cosine of 2 pi is 1. So that's going to be negative 1. Plus, right, minus and minus will give you plus. And then cosine of 0 is 1. And you get big fat 0 as the answer. And you go, whoa, what? It's not 0. Area under curve is not 0. I can color. There is area. What do you mean 0? And this is something that you have to be insanely careful with as you move on through your education. The area you get from Riemann sum or this definite integral is not area under the curve, it's the net area under the curve. And anything that is below x-axis becomes negative area. And everything that is above x-axis is a positive area. And in this case, when they are perfectly the same, they cancel out. So you get a big fat 0. So all of the examples that I carefully picked in 5.2 only had the function above. Remember that triangle was above x-axis and that x cubed function was above, right? Yeah, I picked stuff that was above x-axis because I cheated. Because I knew that the area we're getting is going to match perfectly the calculation. But the trick is that when the function dips below x-axis, it is creating negative area. And then when you add the two, you actually don't get the area because you have actually subtracted some area from it. So there is a big issue here. And you have to be careful about it because now this brings, and then we'll see some formulas next time we're there. We'll see some formulas that will fix some of these things. Now we're going to fix this in a particular way, but there will be more of this in 5.4. So even if we try easier formula, let's say integral of x dx from -3 to 3. Well, I immediately know it's going to be 0 here because I know the graph. Looks like this, from -3 to +3, and then this being negative and this being positive, the net is going to be 0 on the area. So it's geometrically, to me, instantly obvious. But if we go and say, okay, x squared over 2, computed from -3 to 3, which is 9/2 minus -3 squared, which is also 9/2, you get big fat 0. And but we know it's not 0. So how do we fix it? And there is a very easy fix. All I need to do is to bump this up. I need to bump it up. And if I'm able to bump that one up, then I have two positive areas and I just add them. Now, when you have something below x-axis and you want to bump it up, you just put it in absolute value and it bumps it up. This is why we reviewed that on the first day of our course when we talked about f of x in absolute value. And that f of x in absolute value will bump any parts of the function below that dip below x-axis. They will bump them up. So now the question is, and this is like a boxing match or elections, whatever you want to think about, right? It's like a boxing match. What do you need? Do you need area under the curve, or do you need a value for the integral? Because all of a sudden they're not the same if the function dips below x-axis. So for functions that are above x-axis everywhere, like x squared and whatever, right? Yeah, these two concepts are the same concept. But as soon as your function dips below x-axis, you are immediately going to have the you're immediately going to have this issue where area does not match the value of the integral. So here in blood, area under the curve equals value of definite integral only if f of x is larger or equal than 0, meaning positive, meaning above x-axis. Always above x-axis. That's it. That's what I'm going to stop right with this. So, how do we fix this issue? Well, luckily, we had that property last time that told us that we can chop these intervals whatever we want. So my integral from 0 to 2 pi of sine x dx is going to be chopped into 0 to pi sine x dx plus pi to 2 pi sine x dx. Why am I doing that? Because the troublemaker is this second part of sine. 0, pi, 2 pi. This is the one that needs to be bumped up so that I can have a plus and plus calculation, which means I have to put absolute value on that one right there. So now, because that's the one that I need to bring up, right? It's this second bump that was below that I need to bring up, and I just simply bring it up by putting absolute value around it, and it's just up. So now, integral of sine is negative cosine x from 0 to pi plus absolute value of negative cosine x from pi to 2 pi. And when you compute this time around, you will have an answer. So negative cosine pi minus negative cosine 0, that's b and a, right? So you cancel those. I mean, you compute those. Minus cosine 2 pi minus negative cosine pi. Put the values in. Now, for your cosine, it's where the pi is, it's where 2 pi is. So, cosine of pi is negative 1, so minus negative 1. Minus and minus will give me plus, and I get a 1 there. Now remember, oops, I forgot to put this, guys. That's a plus, that's the absolute value, that's a negative. Holy nightmare. Plus absolute value. Negative cosine of 2 pi, that's a negative 1. And then plus cosine of pi is negative 1. So I get is 1 plus absolute value of negative 2, which is 2 plus 2, which is 4. And there is your area. So area under the sine curve and the cosine curve, because they're the same technically, is 4. And isn't that awesome to have like a perfect round answer for area under the sine curve to be exactly 4? It's like amazing, right? You're expecting like pies and all of these kind of things. No, it's 4. It's amazing. So that's it. Now you know how to compute area, and in some calculations you will need the value of the integral. In some calculations you will need the area under the curve, because sometimes we just need the net area. Remember, if I am to compute this as a net and get 0, that answer is still valuable, It's not valuable for geometrical perspective because I want to color, right? But you put in bunch of energy into the battery in a charging cycle, and then you discharge it, which means you lost the energy, and you're at zero because let's say cell phone battery is empty, and energy is the area under the curve. So there is no more there is no more charge. Everything went back to chemical, right? Because the energy, the battery stores energy in chemical energy, and then you charge it, right? And then it converts that into electricity. So when you charge your battery, you supply energy to the system, right? From the grid, from your charger. You pump the energy into the system, and now system has energy. And then when you use your, let's say, cell phone, right? That energy is depleted, and then the total energy for the whole thing is zero. So we do need the value of the definite integral as well. But as I said, sometimes you are looking for area because you want to color, which means that for the function that dip below x-axis, the value of the integral and the area under the curve are not the same value. And it doesn't have to be zero. I mean, it could be off just a little bit. We can see that, right? If I modify my previous example with simple x dx, but I go from -2 to 4, let's say, right? Then when you draw the function like this, you see like -2 and 4. So you have much more stuff that it's above than below. So you're still going to have some net gain, but it's not going to be exact area under the curve, right? It's going to be the difference of the plus side minus the minus side. So when you look at this, it becomes x squared over 2 computed from -2 to 4. So that's your 4 squared minus 2 minus -2 squared divided by 2, I mean. So that's 16, that's 8, minus 4 divided by 2 is 2, is 6, right? So this over here is value of the integral, not area. It is the net area, but we can compute the area this way. Integral -2 to 4 x dx is going to be integral -2 to 0 x dx, and that's the problem piece because it's under the x-axis, so stick that into absolute value, and plus 0 to 4 of x dx. See, now we made sure that all of the areas are positive. So now when I compute this, I'm getting my x squared over 2 -2 to 0 in absolute value, plus x squared over 2, 0 to 4. When I compute this, I get a big fat 0 here. So that's going to be absolute value of 0 minus -2 squared over 2, plus we have our 16 over 2 minus 0 over 2 for the second part when you work that out. So now what you have is absolute value of -2, because -2 squared is +4. +4 divided by 2 is 2, and then you have this negative, so that's -2, plus 8. And this is 2 plus 8 equals 10. Now that's area. To color. So if you are to, use your OCD and draw this nicely, you would be able to calculate exactly 10 squares, right? When you add all of those halves, you will be able to calculate exactly 10 squares to color. But the actual change in energy, right, is not 10, it's 6. So understanding these differences in mathematics, again, later on in physics, make your life better and easier because you want to know that's also the difference between distance and displacement. Like there are so many concepts in physics that you can just fly through like a joke because you understand this. And again, depends on, you know, the way the physics is taught, depends on your level of interest in physics. Obviously, if you're taking general physics, you're not going to see any of this because it's not calculus based. But when you take that analytical physics, right, the engineering physics, where you have physics 1, 2, and 3, like you should see this. And it should be explained, right, the differences between the net and the area and so on. And that's it, guys. So that's your fundamental theorem of calculus, where this part here was pertaining to definite integral, being careful, right, whether you're calculating the area or the net or whatever, using the absolute values to fix, right, in quotation marks, if you have the issues. And then you have all of this other talk here with part 2, which sets the stage later on for differential equations, and literally rest of your life of STEM rests there in that part 2. Very important section. It's a short section, but very important section, and hopefully you will do many exercises to practice this, especially the area stuff. And yeah, questions, concerns, anything? Okay, well, let's say bye.